Good morning, everyone. We are going to start again, and we are going to build on the previous example of the predator and prey model to play a little bit with a package called differential equations. That is one of the best things that happened to me as someone who needs to solve differential equations because it's very fast, it's relatively easy to use, and it has a ton of functionalities. It's a big package. It is a big boy. And so whenever you try to use it for the first time, you will see the little pre-compiling differential equation message that is going to stay here for a little bit. And the reason is this package does everything, pretty much. Everything you want to do with differential equation, every type of differential equations, they're in the package. All of the algorithms, all of the little things that will make your life easier, the little tricks that you can use are implemented in this package. It is the single most comprehensive solution for integrating differential equations that you can think of. So it's taking a while to compile. It has many sub-packages. It has a lot of things. We're going to use that extensively for this class. And so the first time you build a package of this scope, it is going to take some time. That's fine because while it's compiling, we can start thinking about the way we want to express the problem. So I'd like to remove one element from the discussion before we start, which is, if we can write a function that's called dx, and it takes two variables, x and y, which is what we've been doing so far. So let's do that. Let's do it for the logistic model. Let's say dx is equal to r times x times 1 minus x. We know that this is representing the rate of change for a given population that has a parameter r, which is its growth rate, and a variable x, which is its population size. And so we may be tempted to do something like x0 equals 0.1, and then for t in 1 to 1000, x0 equal plus dx of x0, something like that. And it looks like it is matching with the definition of what the thing is. It's a change over time, and so at every time step we calculate the change and we add that. If it's positive, it's going to increase. If it's negative, it's going to decrease. That is a wrong solution. It is a wrong solution for a variety of reasons, but the definition of what a differential equation is, of what a derivative is that the time differential, the dt component, is supposed to be very small. So very small, and then you think even smaller than that, and then even some more smaller than that. It needs to be basically zero, but not quite. If you have looked at the series of videos, The Essence of Calculus by 3 Blue 1 Brown, there is a fantastic definition of what of how small dt needs to be. And what it means is that if we use this naive approach here, which is dx equal this thing, we are working on a dt that is going to be very large relative to what? Well, relative to the change in dx. And so we're essentially taking something that is supposed to be expressed in continuous time, where the difference between two subsequent time steps is almost zero, but we are actually calculating that on a time scale that is much longer. And so it's going to lead to all sort of instabilities, and that is why we do not do that this way. We do not approach the problem in this way. What we do is that we use packages that are going to perform the process of what is called numerical integration for us. It's a good exercise. It's a really good programming exercise. There's a lot of value in it, of taking an algorithm like the Runge-Kutta second order or the fourth order Runge-Kutta method, write that in a general way, and use that to solve your systems of differential equation. It's going to get you to think about functions. It's going to get you to think about auto-write things that are relatively abstracted about manipulating parameters and things like that. And it's going to give you a better appreciation for what goes into actually integrating the formula that gives a differential. That being said, it's not what we want to use. For problems that are even moderately complex to solve, even like RK2 or RK4 are not going to be sufficient. If we have things that are like stiff problems, we have algorithms that are much better. And we don't want to be writing our own version of this algorithm. We want to use a package that is going to do it for us. And in Julia, this package is differential equation. So this is bad. Don't do that. And I say that I've written a paper in my PhD where I used a variant of this method, and it was so much longer than it needed to be in terms of runtime because I didn't use the correct way. But that was more than 10 years ago, so there was no Julia and no differential equations this time. That being said, to use differential equations, we need to define a few different things. We first need to, I'm going to put that here, we'll use that later. We need to define a model. That's not going to be really different from what we've been doing so far when we wrote dx and dy. So let's call that predator prey, and it is going to be a function that is going to take a bunch of different parameters. So we're going to give this function four arguments. That's du, u, p, and t. And these are respectively an array to store the derivatives over time. So that is preventing us from reallocating the memory every time. We don't need to, it's sort of done automatically by the package, but we're going to still specify it and say, please do reallocate the memory instead of creating a new one every time. U is going to be the population size, the state of the variables. It's called U and not X or N or whatever else because that is sort of the standard notation in calculus. When you work with differential equation, it's U. So we're going to let that be U. P is an object with parameters. It can be an array of parameters, it can be a dictionary, it can be a name tuple, it can be a normal tuple, it can be all sorts of things. And T is the time. In most cases, we don't need to use the time. It's not something that appears in our equation. We don't have the growth rate as a function of time, or we don't have the competition as a function of time. But if we wanted to have that, then we could, because the model that we use with differential equation, they have they get access to the time of the solver. Not just the time as being like 0, 1, 2, 3, 4, 5, but the actual precise time at which the system is currently integrating at which a package is currently integrating your system. So that is convenient to have, and we'll also stop mentioning it forever and not use it. So what we need to do then at this point is to write is to put something into du. So du of 1 is going to be the equation of the prey. We're going to put the prey first, and then du of 2 is going to be the predator. So du, the equation for the prey is going to be the prey population size times the growth rate times 1.0 minus u1 minus p times minus p beta times u2. We could do something like x, y equal u and use x and y. We don't really need to do that. So it's like u1, u2. The population size, the population change for the predator is going to be the population size of the predator times p dot gamma times u1 minus p dot delta. Okay, so this function is not returning anything. It is reallocating this du object. So you will notice that we don't create this du thing. It's going to happen internally. measures here. So that is a model that we use. The next step is that we need to create a few conditions for the models to run. So condition number 1 is going to be U0. So U0 is the initial value of the system. So let's say we start with 0.5 preys and then 5 units of predators, whatever that whatever that means. Think of a system where it's okay to have more antagonists than preys, things like parasites, for example. Then we need to define something that's called a time span or T-span. This is going to tell us for how long the system should be running. And we want the system to run from 0 to, 100 time steps, for example. Let me just compile plot so that it does so where we do the rest of the things. And then we have our little, it's here, our little name tuple of parameters. So we have R, we have beta, we have gamma, and we have delta, and they're all here. So that's good. So this is a condition that we will use to run the system. Now the thing we need to define is the problem. Let me add a comment here. Condition to run the integration. Define the problem. So the problem that we need to solve is, we're going to call that prob, and it is an ODE problem. And an ODE problem takes a function first. So our function is going to be predator and prey. Then it takes U0. Oh, that's cool. We have U0. It takes T-span. We have T-span. That's good. And then it takes some arguments. And so the arguments are P here. So that is a problem, a differential, ordinary differential equation problem. In the, not next week, but the week after, when we start working about on epidemiological models, we will see different types of differential equation problems. We'll see stochastic differential equations, maybe not from the first week, but we'll definitely see some stochastic differential equations. There are also partial differential equations, there's Bayesian differential equations, there's all sorts of differential equations. Most of the time when you're reading your ecological modeling textbook, it's going to be ordinary differential equations. So that is a problem, and then this problem needs to be solved. And so the solution of this problem is solve the problem. So the syntax is fairly simple once you get the hang of it. Let's define our function, predator and prey. Let's start with U0, T-span, and P. And we are going to define the problem. So when you define the problem, it gives you this nice little summary. So this is an ODE problem. The type of U is a one-dimensional array with floating point value. The time is defined as floating point value, and it is in place. So in place means that we use du here, and so it's going to rewrite other things. It's going to be, for this specific problem, it's not going to make a difference in time, but for a longer problem, things that are more complex, it is going to be making a huge difference. So we're taking an example here with a single, two populations, which is a very small and simple problem. We are using differential equation in research application where we do things like biomass simulations in food webs that can scale to a couple hundred different species. And it still maintains this amazing performance thanks in part to things like in-place allocation. So that's something that we can use it with two populations, sure, but we can also use it with systems that are far more complex, with far more complex nonlinear functional responses and a lot more components to it, and it's still able to perform really, really well. So that's really, if you do any sort of simulation, that is a must-know as far as I'm concerned. And then we solve the problem. Right. Yes, we solve the problem with the correct variable. So the first time we run something, it is again going to be taking a little bit of time. I really need to stop saying that, but I still want you to make sure that it's not going to be that long to solve a two population problem over 100 time step every time. It's just compiling the thing that it needs internally. The output of solve is it's a specific type again that belongs to the differential equation package, which is a solution. And there are a lot of different little tricks you can do with solutions. You can transform them into metrics. You could do interpolation. The package is really about giving you the minimum amount of information, so it's fast, but giving you the tool to extract information. That's it's kind of mind-blowing how smart that is. And so that is the solution that we get. Let me rerun that next, just to make sure that it is actually very fast. Is it that fast? Yes, it is very fast. Let's time it. Let's time that. Let us do at time. Suppress the output, and that is 5 times to the minus 4 seconds to run that. So you could run a lot of simulation with this system in a very short amount of time. You could run like 5,000 thousands of simulation within a second of your time, which is pretty cool. One thing I'd like to show is that the solution object can be plotted directly. So if we do plot of something that is a solution, it is going to give us the plot of variable values over time, which is something that we may be interested in. So let's have a look at what this specific solution is going to look like. Cool. So that is definitely a thing. So what we see is that we start from our little population size here. It seems to be like 0.1 and 5, I think 0.5 and 5, and then there is an increase in population size of the predator, and then a slight decrease in the population size of the prey. So maybe we need to run this system for a bit longer. Let's say 500, because it's not going to make any difference. So when we run this thing for 500 time steps, what we end up with is something that looks like, let's have a look at the last time step of the solution. So the last time step of the solution is 0.2 preys, and then 43.999 units of predators. Does it look familiar? Well, let's have a little look at the value of delta over gamma, and it's 0.2. And let's actually have a look at this entire diagram here. So predator, prey, yep, that's good. Okay, and what we're going to do is do a plot of, what if we do the last bit of the solution? No, that's not what that, not that. Okay, give me a minute. We want to plot the last, okay, so we do x, y equal last of the solution, and we'll plot x versus y. Huh, interesting. So what we see, and let me change that so it's very, very obvious where we end up. And then no label. So when we run our system and we look at the population size at the last point, we end up on this huge orange point here. And interestingly, this huge orange point happens to be the point where we predicted the system would end up, because that's where the two isoclines are intersecting. So we start from somewhere on this plane at around 0.5 and 5, I think, and we're slowly converging to this point here. So let's try to get a sense of what is actually happening, because we have let's remember that we have this time series, but we would like to see how U1 is changing in relationship to U2. So that is going to be, let me remember the syntax. Yes. So if we want the value of the first component, we can access the solution object directly, like we would with any sort of array, which is cool. So we can do a plot of sol 1, which is the population of the prey, and sol 2, which is the population of the predator. We're going to put that in red, orange is fine, and not give it a label. Oh, you need to do that on the correct plot as well. So here's what's going on. Sorry, I'm going to do some little tweaks here. Gray. Let's put a box on that. Box. That's frame equal box. Let's specify what is an isocline. Oh, yeah. It's dash gray. What am I doing? Oh, yeah. Okay. So we have the population size for the host, population size for the prey and the predator. Then we have the equilibrium point. That's still where it should be. And let's show what the dynamic looks like. So we start from here. And at the beginning, so we can move along this line. And that is the same thing as moving through time in our system, because we end up here. So we start from here. And it's sort of increasing, where it reaches a point where the population of the prey starts to decrease. So it crushes this boundary, but then it gets back, and it gets back to the point where it's not changing anymore. So it's very, very close to this line. And that brings us to a point where, remember, because we are past the predator isocline, we are moving upwards. So we are stuck in this part of the system where we're moving up and left. And so we are moving here and here and here and here, and so we end up around this point of the equilibrium. So let's say we do the same thing, but we are going to zoom a little bit. We're going to say, let me think about the limits for this thing. We are going to zoom on maybe 0.2 to, no, not 0.15 to 0.25. And I don't want that. And then we are going to zoom from 40 to 50. That makes sense. Let's do 42 to 50. 42 to 45. It's fine. So we are really very, very slowly approaching this equilibrium, and then we could zoom in as much as we want, but it's very clear that it's going to be converging to this point. So one thing that we might be interested in um, is it going to be the same thing if we start from different places in the space? So let's say we, instead of starting with a population size that is 0.5 and 5, what if we start with a population size that is 0.1 and 25 as an example? So well, to do that, all we need to do is to change this line here. So new initial condition, initial values. And we are going to simplify the writing a little bit. We're going to solve that directly. And instead of having u0, we are going to get, say 0.1 and then 25. So what if we plot this new solution? It's going to look like it ends up at the same point. So let's do that, but let's now plot it on the same space that we have here. I don't really care about that. So if we start from another condition, we are going to decrease a little bit, cross this boundary here, and then resume the same sort of dynamic where we end up at the equilibrium. So one thing that is usually fairly informative to look at with this type of models is to start from different position on the plane and then look at how the system is changing and where it ends up. So try to see if there is a convergence towards some areas of the graph. So we could do this in a way that is fairly easy, which is we're going to specify our graph. We're going to call it P1. And just remember that graphs are objects, so we can modify them specifically. So that's cool. Let's do P1 here. And then we'll do for x in, we're going to start from, let's do 0.01 to 2. And then let's do 25 steps, and then for y in lean range 0.01 to, we'll do 50, that should be enough, and do 25 steps. What we want is to do this step. So we want the solution to be that, we solve this problem, and our initial value are x and y. And then we plot as on P1 the solution for the first and the second component. We're going to put that in blue and set an alpha of 0.1, which is to say we're going to make them transparent a little bit and no label. Most of the time here is going to be spent plotting, by the way. Plotting is usually, it's plotting something that is difficult for a computer to do, and it's time consuming. It's also difficult to optimize, and so most of the time in sort of loops are going to be spent plotting. But if we then call P1, we are going to see this nice little diagram. And it's pretty neat, because what we see is that some of these initial conditions are approaching the equilibrium in a way that is different than the other. You have some that approach by above and then circle down and then get back to it, and some that approach by below and then end up circling alongside. But they all seem to be converging to the same sort of, to the same point. And the point is the equilibrium that we have identified for this system visually. I am saying the equilibrium, which, as you might have guessed, is a simplification because there are other equilibriums in this system. But for the moment, we are going to say, well, this is the equilibrium that we care about. So that is an interesting visualization, I think, because it gives you an idea of where the populations are, what are the places where populations can be on this space. And so they're going to be following some sort of trajectory to approach the equilibrium. They're not coming to the equilibrium for all of the possible directions. In fact, if we let's say we increase that a bit and we do more, so we make them more transparent, but we do more lines, we should see that emerge even better. That's going to be taking some time. No, it's fine. What we should see is that the system is not approaching the equilibrium from any random directions. There's only a few, like if you're far away from the equilibrium, you can be everywhere in the plane. But the closer you get to the equilibrium, the more constrained or canalized the dynamics of the system become. That has to do with something that is explained in the textbook, where you look at things like eigenvectors of the system, for example. But what is fairly obvious to see here, and we could zoom, and I won't be doing the zoom because it would take a while to redraw everything. But there's sort of a line here, and every population, no matter where it starts, under this parameter value for the system is going to approach the system as the equilibrium from one of two directions. And I think it's very cool. I think it's important to visualize it this way. And what is very interesting that we can see the movement tends to be mostly like horizontal here. That is definitely something that has to do with the parameter value that we picked. And we have 10 more minutes, and I'd like to do a quick exploration of something that's a little bit different. Just what happens if we change the value of the parameters? Can we bring the system to a behavior that looks different? Something that maybe has a little bit more spiraling, not just like converge with a slight curve, but we're actually circling this thing. Maybe we'll manage it, maybe we won't, but by the time you've done the reading for next week, you will be able to do it, definitely. So one issue that we have, let's call that an issue, is that the isocline for the prey is intersecting the y-axis at a value that is very, very high. It's a value of 50. We also know that the isocline for the predator, for the prey, is going by is given by this expression. And so the question that we might want to address is, what is the value of this when x equals 0? So it is going to be PR over P beta. I had it, which is 55. So that's what we get. Okay, so the intercept here is going to be R over beta. It's 55. So what that means is that if we want the system to change the value of the value at which the isocline for the prey is crossing the y-axis, we need to change either the value of R or the value of beta. Let's keep in mind that one thing that is very important is that neither R nor beta are involved in the value of the isocline for the predator. That should tell you something about the biology. Think of it as an open question. Why is the growth rate or the efficiency at removing biomass in the prey not important on the growth, on the position of the isocline of the predator? I think that's an interesting question to discuss. Okay, so we have PR divided by beta is equal to 55, and we would like that to be smaller. Maybe we'd like that to be 1. And so to have this be 1, all we need to do is to set R equals to beta. So let's go with a new version of the parameters. We'll call them Q. And we'll do 0.2 and 0.2. So if we do PR divided by P beta, sorry, it's Q this time, it's going to be 1. So let's do a little plot here. Let's just check that it's working. Instead of, let's call that P2. Let's call that P1, it's fine. It's Q delta divided by Q gamma. And then it is going to be QR divided by Q beta times 1 minus X. And it's going to be 0, 2, and 0, 2. Cool. So we have changed our system in a way that the equation for the isocline of the prey is 1 plus x minus 1. So it's 1 minus x. What that means that we have sort of rescaled our system. So we can do the same thing. Maybe we also want to change the value of delta, just so that this line is a little bit more to the right. So we are going to do that by increasing delta by 2, let's say. Yep, that's fine. Okay. And so now that we have done this thing, we could essentially do the same little experiment we've done here. And we need to also go this time from 1 to 2. Going to go from something very small here. We just want to make sure that we're using the right parameters, and we are only going to do 20, just because we want that to be relatively snappy. And so what we have here, okay, let me just change the opacity of this thing, is a system that behaves in a way that is slightly different. So before we had something that was mostly horizontal, and now we have something that goes like left, but also upwards a little bit. And it tends to be converging here, like very close. The prey is almost extinct. And then it increases again, and so it ends up here. Let's try to do a quick a plot of a solve for any random value we want. Let's do prey start at 1.2, predator starts at 0.6. And so we can see that there is an oscillation. That we didn't have this oscillation before. We had something that was converging, nice and slow to the equilibrium, but now we have changed the parameters a little bit. And the behavior, the qualitative behavior of the system has changed, and we can see this very slight oscillation. There is a mathematical reason for that. It's going to be something that you find out when you will read the chapters on really quantifying the stability behavior and the behavior of systems. But for the moment, let's get back to our plot. And it's a visual way of looking at the fact that we have no different sort of behaviors. And so one thing that is also interesting is that we can see a greater diversity of ways to approach this equilibrium. So at the end, there's still this sort of line here, but the different initial conditions are sort of entering this lane that is going to bring them to equilibrium through different points. And it just goes to show that changing the parameters is not going to change the quantitative result that you get. And that's a big point of why stability analysis is such an important concept. That it is also going to be changing the qualitative behavior of the system, where we move from something that was, let's go to the equilibrium, to something that is, let's still go to the equilibrium, but we're just going to spiral around it a little bit before. And that again is something that we can figure out mathematically what the condition for that are in a very precise way. But that was an illustration of using an ordinary differential equation, visualizing the results, and then developing an intuition for what is going to happen when we are close to an equilibrium. That concludes the second module for this week. We are going again to break for 15 minutes. So we're going to start again at 11:15. And we'll do something that is a little bit different, which is get back to the idea of there is more than one equilibrium in this system. Actually, where are they? and then apply some very small perturbation to get a sense for what stability means from, again, a visual point of view. That's going to be a setup for next week where we go through what does stability mean from a mathematical point of view, but I want you to get a sense of what is going to, what stability looks like. So let's take a 15-minute break, and I will see you here at 11:15.